and then we'll get going here. So we've got, for our first reaction, we have an ionic compound reacting with an element. What kind of reaction is that? All right, single replacement. In a single replacement, we always have to check the element to see whether it is a metal or a nonmetal. Which is it? It's a nonmetal. Sulfur is a nonmetal, so it is going to switch places with whom? With oxygen. All right, so calcium's new partner is sulfur. Oxygen ends up by itself, okay, and it's one of the special ones. Single replacement are probably the reactions where you have to remember the most rules, okay, because you have to remember to check for special elements because there's almost always one. You have to remember to swap and drop ionic compounds, -2, +2, so that compound is okay, and then you have to balance. All right, so we should start with sulfur, present in the biggest number. So I need an 8 there, which gives me 8 calciums. So I need an 8 there, which gives me 8 oxygens. So I need a 4 there to give me the proper number of oxygens. All right, so 1 mark for CAS, 1 mark for O2, and 1 mark for the balancing. All right, number 2, carbon-hydrogen containing compound reacts with oxygen. Combustion reaction. Products? Carbon dioxide and water. All right, so now we have to balance. We always start with carbon, and in this one we apply the rule of 2 because 10 is an even number. All right, so we do that. So I need a 20 here. Okay, 2 times 22 is 44. 22 times 2 is 44. All right, 20 times 2 is 40, plus 22 more is 62. So we need 31 here. Okay, so 1 mark for CO2, 1 mark for water, 1 mark for the balancing. Number 3. We've got 2 ionic compounds. So what kind of reaction is it? Double replacement. So we have to swap the metals in a double replacement reaction. All right, meaning that sodium and iron will be in new places. So we will have, okay, FePO4, okay, and NaOH. Now they're both ionic, so I have to check my drops and swaps. Okay, OH is -1, sodium is +1, so sodium hydroxide is okay. What charge did iron have over here? 3. So it has to have 3 over here, which means that this compound is also okay because phosphate is a -3. All right, so now we got to do some balancing. There's 3 sodiums over here, so I need a 3 there, which gives me the 3 OHs that were present over on the reactant side, so now the equation is balanced. Okay, so 1 mark for FePO4, 1 mark for NaOH, and 1 mark for the balancing. Okay, number 4, 2 elements reacting is what kind of a reaction? Okay, I hope I didn't catch anyone because I did the same trick I did on the last quiz. I put the nonmetal first. Okay, but in an ionic compound, the metal is written first. Okay, it's an old trick, but I'm not very creative. That might be a hint that I might use it again somewhere, like next week on Monday. All right, so we've got -3 here, and nickel is a multivalent metal, but it was an element over here, so I have no way to know its charge, so I pick the most common, which is 2. Okay, so Ni3P2. Now I got to balance. I should start with phosphorus because there's 4 of them over here, so a 2 there and a 6 there will do it. So 2 marks for Ni3P2. Easiest 2 marks ever. Okay, and 1 mark for the balancing. And number 5, only reaction that starts with a single compound is decomposition. So it breaks down into nitrogen and hydrogen, and they are both special, N2 and H2, and now we need to balance. So I've got 3 hydrogens over here, but I only have 2 over there. What's the lowest common multiple? 6. And that should do it. Okay, so 1 mark for N2, 1 mark for H2, and 1 mark for the balancing. All right, now guys, I've been looking over these quizzes as I enter them, and I've noticed that a bunch of you have been giving out half marks. Just so you understand, I don't give out half marks. So if you put half marks on there, they're not getting them. All right, so please don't. All right, they either have it right or they don't. There isn't any half marks here. I just don't want anyone's confidence to be inflated unnecessarily. Okay, so give them a mark out of 15. Let them see it, put it in the box, and then we're going to do some mole equation stuff here in a sec. All right, need you to take out a sheet of paper here, guys. I want you to copy down these 4 questions, and then I want you to try them. They are just like the examples that I went over in class yesterday. Because how many ways are there for me to ask you about the mole equation? 4. This is them. Okay? Or these are they, or however English proper is that you say that. Okay? All right. So give these a try. I'm going to give you a few minutes, and then we'll go through them together as a quick review. Okay? Other point here, quick review. What is the importance of this number? Well, we use it to do that, but what does it tell us? Right. It is the number of particles in a mole. It is Avogadro's number. Okay? It is really important that we understand what that number is because it helps us to know when to use it. If it tells us the number of particles in a mole, it will help us to either find the number of particles or, if given the number of particles, find the number of moles. Okay? That is its purpose. Its purpose is only to be used when you need or are given the number of particles. You either need the number of particles or you are given the number of particles. Then you must use Avogadro's number, which is the number of particles in a mole. All right? Remember that the formula, the mole equation, is N equals little m over big M. N is the number of moles. Okay? Little m is the mass in what units? Grams. All right? And lastly, big M is molar mass, all right, which you get by adding the numbers from the periodic table together for your compounds. Okay? All right. Give you a couple minutes there. All right. So for question number 1 here, how many moles of calcium carbonate are there in 125 grams? So our first step is always to write down what the question has given us. They gave us the mass, 125 grams. And they gave us the ability to calculate molar mass because they told us that it is calcium carbonate. Okay, that means 40.08 plus 12.01 plus 16 times 3. Okay, so 40.08 plus 12.01 plus 48 is 100.09 grams per mole. Okay, can I find N, the number of moles now? Yes, and I don't have to manipulate the equation. It's already set up for that. N equals little m over big M, 125 over 100.09. Okay, and we get 1.25 there, right? I would think, yeah. 1.25, and what are my units going to be? Mole. Okay, so that's a 3 marker. 1 for the givens, 1 for the math, 1 for the answer. Okay. Questions on number 1? Okay. All right, question number 2, and again, guys, remember that I told you yesterday on the unit exam, and probably on a quiz, I will not give you the formula. All right, I will write it in words and see that you can do your swaps and drops and write formulas correctly. All right, they give us in this one the number of moles. And they give us the ability to calculate big M because they tell us that it is Li3P. So we got 6.94 times 3, okay, plus 30.97. All right, so 51.79 grams per mole. Okay, so now I have little n and big M. So n equals little m over big M, and I need to manipulate to get little m here by itself. So I multiply both sides by big M. It cancels on that side and appears over here. So 1 mark for your manipulation. All right. And you'll get 1 mark for plugging in the numbers correctly. So that's 51.79 times 2.7. And our final answer, okay, is 139.83 grams. Sorry, no, I lost. I got 139, not 189. 0.83, right? Grams. Okay, so that's a 4 mark one. All right, questions on those two? Okay, how many people are done number 3? All right, I'll give you a little bit more time. Remember, number 3 has an extra step involving what number? Avogadro's number, right? Okay. So on number 3, okay, we're looking for now the number of molecules slash particles, okay, of Fe2O3 that are in 230 grams. All right, so again, we write down our givens here. We were told the mass, 230 grams, and they tell us what the compound is. So with Fe2O3, right, that will be 55.85 times 2 plus 16 times 3 to get the molar mass. Okay. So 55.85 times 2 plus 48, okay, is 159.7. Okay, grams per mole. All right, even if you weren't sure where to go to get the particles, what should you calculate right now given what you have? Moles. Okay, at least go that far. Remember, never stop, okay, at this point. If you know you've got 2 out of the 3 things in the mole equation, then it's probably time to do the mole equation. All right. So we got to plug in here. So you got 1 mark for your givens, and we're trying to find the number of moles now. So that's going to be 230 grams over 159.7 grams per mole. Okay, so we got 1.44 moles. All right, so 1 mark for that step. Now, at this point, we have to use Avogadro's number because now we're dealing with number of particles. If I know the number of moles, and I know how many there are in a mole, what do I do with those 2 numbers? Multiply, right? Okay. All right, so to get the number of particles, I take n and I multiply by Av's number. Okay, so that's going to be 1.44 times 6.02 times 10 to the 23. All right, so we'll take that number and multiply it by, in brackets, 6.02. Second function, hit the comma button, okay, and 23. And we get 8.67 times 10 to the 23 molecules. Okay, I would also accept as a unit particles, okay, because while that's not as accurate, it's still true. Okay. So, mark for that step and a mark for the final answer. That's a 4 mark problem. Questions on number 3? Julia. Round to 2 decimal places in general. If you didn't round, like you had a bunch more numbers after that, that'd be fine. As long as it's the right numbers, I'm okay with it. Okay. Well, we may get to talking about significant figures in physics. Okay. All right. For number 4, we are looking for the mass of 5.42 times 10 to the 21 particles of nickel 2 nitrate. Now, is that more or less than 1 mole, just looking at that number? less. In fact, it's on the order of less than 100th of a mole. All right. 1 mole is 6.02 times 10 to the 23. This is 10 to the 21. Okay, that's 2 decimal places back. That's 100 times less. Yes? Everyone follow me? All right, so we're going to get a very small number here for our number of moles, a decimal, or maybe your calculator might have even spat it back to you in scientific notation. It was so small. All right, so let's have a look first. Here's what we know. Number of particles. Okay, equals 5.42 times 10 to the 21. And big M for nickel nitrate, nickel 2 nitrate, sorry. Okay, so that's going to be, what's nickel, 58.69. Okay, plus 14.01 times 2 plus 16 times 6. So 58.69 plus 28.02 plus 16 times 5. It's 166. Sorry, times 6 plus 182.71. Everyone good with that? Grams per mole. All right. If I have the number of particles, I'm trying to find mass. I need N in order to do that. If I know the number of particles and the number of particles in 1 mole, how do I get the number of moles? Divide them, okay? It's like taking 36 over 12 tells me I have how many dozen? 3. Okay? Divide the two numbers you have. So, to get N, I'm going to take the number of particles, 5.42 times 10 to the 21, over 6.02 times 10 to the 23. Alright, so in brackets 5.42 E21 divided by 6.02 E23. Whoop. That didn't work. Okay. Alright, so we get 0.009 moles. So a very small number of moles. Okay, in fact, it's less than 1/100th of a mole. It's only 9 thousandths. Yeah. Okay, so that's not so good. So a very, very small amount of moles. Now that I have N and big M, can I find M? Yes. All right, so N equals little m over big M. I multiply both sides by M to get N, little m by itself. So we plug in our numbers here, and we have 0.009 times 182.71. And we get 1.64 what? Grams. All right, so 1 mark for the final answer. Okay, 1 mark for your manipulation, 1 mark for your plugging in of numbers, okay, and 1 mark for this calculation here, and 1 mark for your givens. 5 marks for that question. Okay, is that ringing a bell for everybody from yesterday? All right, now the worksheet I gave you yesterday, the first question, did you need to use the mole equation? No, you did not. Okay, and all it was asking you was if you understood what Avogadro's number was really all about. Okay, so if we're looking at that first page of the worksheet here, okay, it asked us how many atoms or molecules are present in each of the following. How many of anything in 1 mole? Right, Avogadro's number. It doesn't matter if it's gold, hydrogen, okay, it doesn't matter. It's 6.02 times 10 to the 23. How did I do that? I went 1 times 6.02 times 10 to the 23. Anytime we're figuring out number of particles, we multiply the number of moles by Avogadro's number. Okay, so if I want to do letter B here, it's going to be Avogadro's number times 2.5, and so on down the way. All right, for number 2, you will have to use the mole equation. All right, because they give you the material and the mass and ask for moles. Okay, so once you get past number 1, then you're using the mole equation again. Okay, questions so far on this worksheet? All right, let's get to work, see how far we can get. If you have questions, let me know, and we will go through them. Okay, so on question number 6, okay, this one sometimes gives people a little bit of trouble because of the wording. All right, it's asking how many oxygen atoms are in 64 grams of oxygen gas. Okay, remember, oxygen gas is a molecule that is made up of how many oxygen atoms? 2, all right, which is why probably the first time you did this, you got half of the number that was written on the key. How many people did that happen to? Okay, it's okay to admit it happens to a lot of people. Okay, so what we're looking for here is we first off have to find the molar mass of oxygen gas, which is 32, right? Oxygen is 16. Oxygen gas, which has 2 oxygen atoms, is 32 grams per mole. All right, we know the mass, so we can find the number of moles. The number of moles is 64 over 32, which is 2. All right, 2 moles. Well, now I multiply that by Avogadro's number, 6.02 times 10 to the 23, and I get 1.204 times 10 to the 24. But that's the number of oxygen molecules. Okay, so I have to multiply that again by 2 because every oxygen molecule has 2 atoms in it. The purpose of this question is not to confuse you. It's just to see if you understand the difference between a molecule and an atom. All right, that's the whole purpose of that question, is to see if you understand the difference between a molecule and an atom. Oxygen is a molecular element. It comes as a pair, which is why the number is twice what you thought it should be, 2.408. Okay, times 10 to the 24 atoms. Okay. Yes. Theoretically, yes. The equipment is very large and probably would not work underwater. You would need some sort of thing that could separate the carbon dioxide. Essentially, you'd need a high-speed plant that could photosynthesize, rapidly produce oxygen from the carbon dioxide that you've exhaled. Right? Problem is, if you're really, really deep, there's not enough light for that to happen, and plants don't do it that fast. Okay, things like that. The biggest problem that divers have is actually the bends coming up too quickly and having all the nitrogen bubble out. Okay, yeah. No, you don't throw up your lungs generally. You get really severe cramping, and you can get, if the bubbles get big enough and they lodge in the capillaries of your brain, they will break the blood vessels in your brain and cause an aneurysm or stroke. Okay, that's the biggest worry. So if divers come up too fast, the pressure decreases really rapidly, and all the nitrogen that normally is just dissolved in your blood and does nothing starts to become a gas in your blood. So instead of being dissolved in your blood, it becomes bubbles, and that is really bad for you, and it's extraordinarily painful. All right, imagine like the worst muscle cramp you ever had. Now imagine that all over your body, including your head. Okay, like in your brain. All right, exquisitely painful. All right, and very, very dangerous. What they end up having to do is throw them in a hyperbaric chamber, which is a big metal tube, kind of like a coffin. Kind of scary. Okay, where they just increase the atmospheric pressure on you and force the nitrogen back into your blood to make it not be a gas anymore, dissolve in your blood, and then very slowly decrease the pressure back to normal so the bubbles don't form. The reason you get the bends is you come up too fast. Right? Happens to astronauts too. That's why astronauts will pre-breathe pure oxygen before they get in their suits, so that there is essentially no nitrogen left in their blood. It's all oxygen, right? And so then they don't have to worry about that. If a quick change in pressure happened, you know, they'd have time to patch their suit or something without real worry. Yes, part of that's the swim bladder, and part of that is, yeah, it is a similar process, yes. More of it has to do with the swim bladder, which isn't, it's like a lung, but they don't use it to breathe with. They inflate it and deflate it in order to sink and be increasingly buoyant. Yeah.